Okay, so in this problem, we have another coupled system. We have a mass, I'm going to call it capital M. It's attached by a string to another mass, small m, and this small m is on an inclined plane, and it's being pulled up the ramp, and we're going to assume there's no friction for this problem. I'll leave it to you to figure out what happens when there is friction. So we're going to draw free body diagrams for both of these objects, little m and big M, and they look like this. Please remember, we always draw the forces in the direction in which they act. So gravity acts on this mass straight downwards. So we draw this force straight downwards. The tension pulls up the ramp, and the normal force acts perpendicular to the surface. And this angle, 25 degrees, is also the angle between gravity and the negative y direction. Since this mass accelerates up the ramp, we're going to call this direction the positive x direction for this component of the system. Okay? All right, and then this object right here is pulled on by gravity. Gravity exerts a downward force of capital mg, and the tension pulls upwards. So just like we've done before, we're going to apply Newton's law to each part of the system. So I'm going to start by applying Newton's law to little m, that's this one right here, in the y direction. So this is the x direction, so the y direction is like this. And that's going to tell us that the normal force minus the component of gravity that's going in this direction, so that's mg cosine theta, has got to equal 0, because this system does not accelerate in the y direction. Remember, the y direction is perpendicular to the plane. So it does not accelerate. So there's equation 1. Okay? Now let's apply Newton's law to this problem in the x direction. Okay? So in the x direction, we have t to the right minus the component of this gravity force that's acting to the left. So that's the little component right here, and that's mg sine theta. And the net force must equal the mass times its acceleration. So this object is accelerating up the ramp. Its acceleration is a, and so the net force, T minus mg sine theta, must equal ma. Let's call that equation 2. We can now apply Newton's law to this problem. Since this mass falls downwards and accelerates downwards, we're going to call this the positive x direction. And so we're going to have mg minus t equals this m times a. It's going to look like this. Capital Mg minus t equals capital M times a. Okay? Now, our goal is to find the acceleration of the system. So we need to eliminate the tension. So probably the easiest thing to do is to solve equation 2 for t and then substitute that into equation 3. Okay? So I'm going to solve equation 2 for t. I'm going to substitute that into equation 3. So when I solve equation 2 for t, this is what I get. So that's this equation here, solve for t. I'm going to substitute that into this equation, and that will eliminate t. And we will have mg minus t, which is ma plus mg sine theta, so that's that, equals m times a. So I'm taking equation 3, and I'm substituting in t, and it gives me this mess right here. Okay? So we've eliminated the tension t, and once we've done that, we can solve what remains for the acceleration. Okay? So that's our goal, to solve for the acceleration. So I would distribute the negatives here. So it's going to look like this if I distribute the negative in front of this parenthesis. Get all terms with an a on it on one side, so this has an a in it. I need to get it to the other side, so I'll bring it over here. It'll become positive. I can now factor a out of this expression, and then I can divide both sides by the sum of the masses, and I get that the acceleration of this system is m, the hanging mass, times g, minus mg sine theta, all divided by the sum of the masses. So there is an algebraic expression. You could then plug in your numbers, and you get 3.83 meters per second squared. And then if you need to find the tension, you have already solved equation 2 for t. So once you know the acceleration here, you can plug it in, and you can find t. So to find the tension, just use equation 2, and you can figure that out as 23.9. Okay? So that's an example. So the key here is to make sure that whatever direction the object accelerates, that is the positive x direction. okay? And then apply Newton's laws, you'll get a system of equations which you can then solve for whatever it is you need to find. Okay, that's how you do it.